Alrighty there. Hey everyone. Hope everyone's doing well. We're back with another little live stream today. And yeah, so today we're going to be following up on something that we talked about briefly probably like 2 or 3 months ago now, which is doing SIMD operations in the Jai programming language. And this is kind of a fun opportunity because I get to sort of try doing everything from scratch. I've thought a bit previously about like, oh, if I were to write my own SIMD library, how would I do it? And in Jai, there currently is no SIMD library, so I've kind of just gotta do it. Yeah, so that's what we're going to be doing today. And yeah, hopefully it'll be a fun time. We'll get into some fun things. So let's get a few things open so that I have some references to look at for when I run into trouble inevitably. Cool. So let me put my terminal over here. And yeah, so I can kind of show you what I've got going here at the moment, which is basically we have this float 4 data type, which is four numbers, in this case 4 floats. I forget if we decided this is float 32 or float 64. Probably we should say float 32. So the idea here is that we've got these 4 numbers. They're in this struct, so they're kind of batched together. And then we can write out our SIMD operators for the data that lives in that struct using some assembly instructions. So basically, this is how we would add an X and a Y and end up with some Z number here that we're going to return. And we're using the add PS instruction, which is kind of the x86 machine instruction for doing a SIMD add. And then we're kind of doing a similar thing here where we have a scalar number and we're adding that to a batch. And we can use this symmetric thing to define it so that the operator works both ways. So we can do float plus batch or batch plus float. So either way will work. So let's see here. Let's try out a few things here. So first, let's just try running some C code using the same kinds of intrinsics here and just seeing what comes out of it. So I don't want to execute. I'm going to make sure I'm not using any libraries here to make this a little faster. So let's say auto add, and I'm going to want to add these 2 M128 data types, which are single precision 32-bit float. So let's see. A and B. We're going to return, well, I gotta think about how I can do this here. Okay, so I can just call it directly. And return that. So right now it's kind of doing a lot of stuff here, but if I turn on optimizations, then this should simplify to just being add PS of those 2 things. So yeah, I'd imagine that this code should compile to the same thing, which is kind of nice. And I'll specify float 32 just to be a little bit more precise, but that's what we want to do here, float 32. Yeah, and so when I run it, when I run my code here, basically what I'm doing is constructing a float 4 batch, printing it, constructing another one, printing it, and then going through a few basic operations here. So I can do x plus y, I can do x plus 4, and I can do 4 plus y. And all of those give me the output that I expect to see over here. So that's kind of nice that we can go through these basic tests. So now let's look at this float plus batch kind of situation and see how would we do that in the plain intrinsics. So now we can no longer do this because we've got like what do you call it? We've got an M128 here and we've got a float there. So we need to, it's called broadcast. There are things called broadcast, but I don't think they're what I want. Here we go, set PS1 is going to broadcast A into all of the elements of our SIMD register here. So I'm going to do so B, we call this B broadcast equals set PS1 B. I think I got that right. Let's see here. Set PS1. Okay, there's a. Oh, yeah, that's right. Okay, B broadcast there. So now that should work. So now I've got this shuffle PS business. I wonder how that would work here in Jai. So let's see. Instead of doing this the way that I've been doing it, actually let's comment it out so I can come back to it if my current version fails. Let's try this. So let's start with X like we were doing before. And then let's start an assembly block. And what I'm gonna want to do here is do shuffle PS. Oh, hey, that's kind of cool. I didn't know VS Code did that. I guess it just gives me the definitions of all these assembly instructions. That's super nice. So let's see. So I feel like I can't just do this, right? Like that. That's not quite right. But let's see. And PS results. Oh, okay, I think I've got this. So instead of doing this, I can just say result is a uninitialized batch 4. Right, and then so how do I get? Yeah, how do I get this broadcast business to work? It seems like let's see. Selects a single precision floating point value of an input quadruplet using a 2-bit control and move to a designated element of the destination operand. What if I just do this? I feel like that's wrong, but you know what, let's try it. Okay. Form was provided, but expected one of vec mem Okay, I see. So vec GPR IMM8, whereas really I want something a little different. What if I do this instead? Matching instruction form is not found. Let's figure out what SHUF-PS is doing in a little more detail here. So, yeah, I guess I need to figure out a more convenient way to get Y here into a SIMD register, and that's kind of what I was doing here, but I didn't love that. I didn't love that approach. I don't know. It seems a bit. I don't know. It seems a bit, first of all, inconvenient, and second of all, maybe not that fast. I don't know. Maybe I'll just leave it that way for now and just kind of keep building up my little SIMD library from there. So yeah, that's what we've got so far. So that works. So let's just keep building from there, and then we can come back and maybe clean up some of these things later. Not sure what that warning's about, but whatever. Anyway, cool. So I think next it would make sense to do, well, if I remember right, operator plus equals should be defined for me. So if I do x plus equals y, and then do some more printing. So here, x plus equals y results in whatever this new value of x is. And then let's also do x plus equals 4 and see if that works. All right, so x plus equals y, that gives me what I expect, and then plus equals 4 also gives me what I expect. So that's kind of nice. Instead of having to define a massive number of operators, I can just define these two, and that'll give me all of these operations for different types of addition that I might want to do. So that's kind of neat. So let's structure this a little bit differently here. So this will be the addition example. Now let's do subtraction. So let's start with the same kind of idea here, except instead of doing x plus y, we'll do x minus y. And I'm guessing this won't work. All right, yeah, procedure call did not mention any of the possible overloads, so that makes sense. I just haven't actually implemented this yet. So let's do the minus operator, and I think it's just sub PS, but we can find out here. Subtract sub PS, yeah, so if I do subtraction, so let's see what we got. We got sub PS, that's what we would expect. So there we go, sub PS, and I imagine this should just work. Oh yeah, okay, I wrote my string here incorrectly. There we go. All right, so we've got plus and minus, And now let's try the rest of these examples here. So let's try minus a scalar minus a batch, and then these sort of I don't know, they call them postfix operators for this way of doing things. There's like a name for that, but I don't remember it. All right, yeah, so we've got to implement the scalar version as well. So let's see here. So now this is kind of interesting because I'm not sure that symmetric is going to work here. We're gonna have to try this. So kind of my hunch is just to do this. I feel like that may not be the right way to go, but let's see what happens. All right, so x minus 4 gives me that. 4 minus y gives me that. Is that correct? That is not correct, right? Because this should be 4 minus 1. So that's not right. So this operation cannot be symmetric, which makes sense. So this is going to be, let's say x is a float 32. And y is a batch 4 of float 32. And so now we want this, right? We just want plus that, and we want to subtract y from x. So that, and see where we get. Where did my mouse go? Cool. So now when we have 4 minus a batch of 1s, we get 3s. So that's correct. And then let's check our other operators here. X minus equals y. So we're subtracting 1. That gives us the same thing we had there. Cool. Minus equals 4. That looks correct also. Hey, Bo. Yeah, thanks for tuning in. Definitely watch later if you got time. Yeah, this will be up online. I guess whenever I'm finished, so probably shortly, or like in an hour or two. All right, cool. So we've got subtraction down, and next let's think about multiplication. So let's see. This one should be a symmetric operation, so we should be able to get away with just 2 operators here. Let me put a few comments in just to keep things organized here. Oops, subtraction. Right, and so now cool. So now we want to do our multiplication operator. So this should be pretty straightforward, just mod PS, unless I'm pretty sure there's a way to directly multiply a float by a register. No. Okay, I guess there's not. That's fine. Cool. So that should be pretty easy. Just to throw that in here. So let's see, x times y, x times 4, 4 times y, x times equals y, x times equals 4. Let's see if we can get these knocked out here in one go. So we'll do multiplication. All right. Let's see, 1, 2, 3, 4 times 1, 2, 3, 4. I guess I chose a poor choice of example data. Let's try that. All right, so 1, 2, 3, 4 times 2 is 2, 4, 6, 8 times 4 is 4, 8, 12, 16. 4 times y is 8. X times equals y is the same as x times y. And then x times equals 4. Yeah, that all looks correct. Cool. So now finally we've got division. Division's the, I don't know, maybe not the hardest one, but kind of the most annoying one in some ways. The hardest one for the computer to do, that's for sure. Yeah, don't do division if you don't need to. Now, do we want to define an operator for a SIMD batch divided by a scalar? Because I feel like in that situation, you might as well just do 1 over the scalar. Yeah, let's not define that, and just define. So we'll define a scalar divided by a SIMD batch, but not the other way around. So let's see here. We've got the div ps, and then here's where we need to be careful, because we want to define this operator for x as a scalar divided by y, which is a batch. And now we can divide by y, I guess. Okay, so probably this isn't going to compile right because this is not defined. So we'll say intentionally not defined. Let's try that. All right, still missing one. X divide equals 4. Well, okay, so let's do a counter example for that one. Float 32. I'll call this Z. Float 32. And then we'll do Z divide equals X. So this will be 4 divided by whatever's in X at that time. 4 divide, well, it's kind of a misleading way to write it, but whatever. Okay, still a bit of a mismatch here. Well, yeah, okay. I guess it's having trouble with this one. Let's just not do this one. I'm not sure it really matters that much. Hey, George, thanks for tuning in. Doing some SIMD stuff today. All right, so we've got x divided by y, 4 divided by y. Where did that really come from? 4 divided by y. Oh, right, that came from this operator. Cool, yeah, so we've got our basic arithmetic operators. That's cool. So let's see, what else do we want to define here? We've already kind of got like most of the stuff that exists in a juice, the juice SIMD register class, as far as most of the math operations. I think I'm going to rename this stuff a little bit just because I would like to be able to like modify individual things inside the SIMD batch without having to get fancy and do other stuff. So let's rename that. I don't think that should make a difference. And so now I think we're ready to do some more types, maybe. Yeah, I wonder also if there's a way to do like kind of specializations for this, because I'm imagining that for like, you can imagine for let's just write this out for a sec. So batch for float 32, right? I'll make it 30. This is a struct. So if I had a batch for floats, I would want to do it like this, right? The way that I've got it, where I've just got 4 floats, right? However, if instead I were to have a batch for of float 64, I might instead want to do it like x0, x1 is a batch 2, right? So I could kind of compose these batches. I don't know, that seems like overkill. Yeah, because I mean, the data themselves isn't going to matter so much. It's still going to be 4 numbers of this type. It's just going to be a little bit of a difference in terms of how I do the operations, but I'm going to have to do the operators differently anyway, so I don't think it matters. So let's maybe reorganize this code a little bit here. So here's our little SIMD module, and I'll put a source folder in here. And so this will be batch 4. I just want to call this batch 4 float jai. I don't know, that's a little bit misleading because it also defines the operations for that. So I don't know, maybe we arrange this somewhat differently. I'm trying to remember how I structured things in some of my other modules, but I'm having a little trouble remembering. So okay, so I don't pull in anything from other files. I just assume that's already been defined. All right, so I know how I want to do this then. So this file is all going to be operations that happen on batches of 4 floats, right? And just to be extra clear, let's call it batch 4 float 32, since that's kind of the jai way. And then I don't know that I even need basic here. I think I can just do, well, let me see. How did I do it here? Yeah, okay, I just started loading the files. So load source. Well, I guess the order doesn't really matter. So yeah, 32 jai. So, and then let's make another file. This will be types. And so I'll put this type in here. So we can have types, and then we can add batch 432. We'll do whatever operations we want in there. And so now, if I go back and run my example again, oh, didn't mean to do that. All right. If I go back to my example, okay, I missed some semicolons. Cool, there we go. So now we've got a basic kind of structure. So I'm kind of thinking for types, I'm going to want a batch 2, a batch 4, and then a batch 8, maybe. Yeah, let's think about this. So let's do batch 2, batch 4, batch 8, and a batch of 16. So 3, 6, 7. I guess I could do these with arrays. I don't know that it really makes much difference. Yeah, maybe arrays would be better. Let's do arrays. So we'll do, what is it? X, T. I know I got my syntax wrong, but I'll have to go back and figure it out here. Arrays, what is the array syntax? Okay, so you do brackets and then that. All right. Maybe I should even just like call these something sillier. I don't know, something like that, just to kind of make it clear that you're not really supposed to touch this. I don't know, but I guess it's like fine if people touch it. So maybe I shouldn't do this. I'll still give it the full array treatment for all of these types. All right, cool. So let's see if that still works. I feel like I probably messed something up. Gotcha. Okay, so if I do it that way, then I have problems using struct literals. Okay. Yeah, let's go back then and just keep it how I had it. And I feel like there's probably a way to go in between, but I don't know it yet. So I'll just do this for now. And oops. Cool. So I've got my 16. Now I need to think a little bit carefully about how I'm going to do my batch 2. Because I want to be able to have a batch 2 of float 32. But if I were to try to do that in its current form, I would run into some issues. So let's see, if I were to just do batch 2 float 32, right? And now I just copy maybe some things from here. So let's just copy over the addition, and then I'll go ahead and do that. Oh, we need to do that. All right. So let's go back to our addition example, and maybe we do, let's just define another little type alias here. So this will be float 2. So ideally, this should just work, but I don't think it's going to. Oh, partly because I didn't finish defining my things here. All right. with that. Okay, error, the variable doesn't fit in a register. That's kind of what I was expecting, right? So the problem is add PS is expecting a register that's, I guess, 128 bits wide. And the register that we gave it, or the data that we gave it, is it has two float 32s, so that's 64 bits, which is too small. So basically what we're going to want to do is pad this. And I think there's a way to do this in Jai. So this is kind of a funny thing that I'm not sure exists in C++, or I guess you could do it with like a template specialization or something. But it's this thing called insert. Insert directive lets you insert compile time generated code or code that has been represented as data in some other way. So let's see. We have a struct example. Struct, okay. I want to put it here. We can make a struct that generates default values for its array, and those values go into the struct's initializer. Yeah, so this is kind of neat. Basically, we're generating the code as a string, and then we're just printing it into the struct, basically, so we can get some sort of compile time code generation. I think this is closer to what we want. No, this is still doing kind of initialization stuff, right? Set diagonals to 1. Elements, something equals 1. Okay. Let me see if I can find this. Let's see. So basically what I'm going to want is, where's my types? Open now. Okay, so I want to do an insert. So let's see. If I think I need to do type info, right? Type info t dot type not equal to float 32. Then return right. So if we're working with any other type, we don't want to modify our struct at all. However, if it is a float 32, we want to do something like this. So but we want to return this as a string, right? And then we want a semicolon, right? Yeah, semicolon. There we go. All right. So, okay, type mismatch. Although I wonder, why do we even need type info? Couldn't we just use a type directly? Okay, so that works. However, we have this issue with our struct literal again, where the things in the struct literal don't fill it up. That's kind of annoying. What if I give it some default values? I'm forgetting how to do some things here. Always struggling to figure out new things here. So I think this is array literals, right? let's see. How do we initialize the array in the same place where we define it? I thought there was a tutorial specifically on array literals, but maybe there's not. Oh, here we go, array literals. Oh, got it. So I have to do this. Oops. So maybe that'll work. Float 32. We were looking for values to assign to this entry when we ran out of values. So I think maybe there may not be a way around this, but maybe there is. Well, I think I started at 0, right? Let's see. That's not what I wrote, though. Oh, here we go. Okay. Type mismatch, wanted unary dot dereference, type given, float 32. Let's look again at the struct literals tutorial and see maybe if we've got an idea here. Oh, okay, I got too fancy with what I was trying to do here. I can just do this. I don't need the extra dots. And let's try that. So that seems to work. Not my favorite way of doing it, but seems like it works, right? Yeah, okay. Let's look through this tutorial again and see if maybe there's a way to let things kind of default. There may not be. Yeah, I might just have to live with that. That's okay. That's not the end of the world. So I have to do the same thing here. And x1 equals that. And there we go. Cool. Okay. So yeah, every float 2 or every batch 2 of float 32 is going to have this extra data padded to it. I wonder if there's just a way to pad stuff without having to actually put data there. I feel like there might be. It seems like the kind of thing the Jai folks might want. Align. So apparently there's ways to have like data members of structs be aligned. I guess this is aligned by bytes, right? Let's see. Let's try a few things here, see what happens. So we get rid of our insert block. Instead, we add a alignment specifier on the first thing in our struct. Does that change anything? No, we still have the issue where the variable doesn't fit. Okay, so we're able to define a struct that has no padding. But are we able to define a struct that has extra padding? Extra padding. Okay. No, expand is not what I want. Unfortunately, there's a ton of things called pad. All right, well, can't seem to find anything right now, but keep my eye out just to see if there's a way to make this work. And for now, I'll just live with what I've got here. So figure out if there's a simpler way to add a struct. Cool. But anyway, so now we've got batch 2, batch 4, batch 8, and batch 16. And so now we just kind of need to fill in the operations for all of those types. So yeah, let's go ahead and go through it. It might be a little bit monotonous for the moment, but by the end of it, we should have a lot of cool things. So here we go, basic SIMD. So right now, we can do addition. Let's see if we can get subtraction going too. So I'm guessing that batch 4 float 32 and batch 2 float 32 will be basically the same. There will be very little difference here, except for, namings of things. So that shouldn't need any modification. This one will need the struct literal specifiers. Yeah, so at some point I'm going to have to go through and actually do some benchmarking, and I've been trying to think about what's the fairest way to do that. Kind of what I wanted was to just get a Godbowl sort of situation running, but I haven't figured out yet how to generate assembly code from Jai. I've heard that it's possible on Linux, but I haven't heard anyone doing it yet on Macs. So I don't know, that might be kind of a challenge, but I'm excited to try it if I'm able to get it working. Oops, need to do that. All right, so here we go. We've got batch 2 of float 32 ready to go. Oh, spelled some things wrong. That's how it goes. Batch 2, whoops. Cool. So now let's just dump in all of the examples here. Subtraction, subtraction, multiplication, and division. So as with before, I'm going to have to go through and kind of rewrite some of these batches. Let's see, x0 equals that. Oh, did not mean to do that. So let's see. 0 equals that. X1 equals that, and then everything else can go away. And then, yeah, same thing with multiplication and division as well. Sweet. All right, so now we've got addition, subtraction, multiplication, and division defined for float 2. So what do we got here? Oh, whoops, I didn't switch these over to float 2. I wonder if maybe I should just define a float alias or like a batch alias or something, just to kind of cover everything for now. All right, so now we've got everything on float 2, and yeah, it looks like we've got addition working as expected. We've got subtraction. Is that correct? Yeah, that's correct. Awesome. All right, multiplication, that looks right, and division. Yeah, so we're gonna get some nans, but whatever hangs out in this extra data shouldn't matter if I'm remembering right. So for now, I'm just gonna try to get kind of these basic math operations going, but I should make a list of to-dos. So comparison operators. So I'm thinking like greater than, less than, oh. Equals, right? And so the trick with those comparison operators is that you can, basically the correct thing to do would be to return like a batch of Booleans. And then, you need to figure out, or the caller needs to figure out what they want to do with that batch of Booleans, right? Do you want to know if all of the things in the batch are equal? Do you want to know if any of them are equal? Do you want to know which ones are greater than and which ones are less than, kind of that sort of thing. So I'll have to think a bit more about how I want to do that. I think I want to do some kind of complex batch. So if I want like a complex number, I want to be able to handle that. I'll have to keep thinking about how that might work. Also, we've got more fancy math operations. So sine, cosine, square root, and so on. Let's think about how and where those should be defined. And then let's see what else. I feel like there's going to have to be some kind of a way to figure out some way of figuring out the best available architecture in the host machine. I'm not sure about that. And then of course, ARM. So right now, I'm not even sure it's possible to compile Jai code for like an ARM Mac or something, but we'll get there when we get there. Anyway, cool. So we've got batch 2 and batch 4 working. Should we do batch 8 next? Maybe I'll wait on batch 16. I'm not sure that one really matters for now. I'll hold off on batch 16. Cool. So we've got batch 2 with our inserted padding. We've got batch 4, and now we're going to do batch 8. So there's a part of me that wanted to do batch 8 as like batch 4, right? So you would have like x 0 x 0, 1, 2, 3 should be a batch for of t, right? And then x 4, 5, 6, 7. But I don't really want to do that. That seems, I don't know. That seems kind of tricky. Yeah, especially with like the struct literals and stuff. So I'll have to think more about this. But for now, let's just do that. And we'll stick with float 32. And you know what? We're going to assume that AVX instructions are available because why not? I'm probably not going to actually use this code in like production for quite a while. So by then, hopefully AVX instructions will be pretty ubiquitous. All right, so I should be able to just copy paste my batch for stuff and work with that pretty easily here. And then make sure I add that to the global module file. Awesome. So first off, let's replace batch 4 with batch 8. Cool. And then anywhere that I'm doing this, I just need to add some more. So I've got 1, 2, 3, 4, 5, 6, 7, 8. Or 5, 6, 7, 8. Yeah, again, I'm not totally sure that's the right way to do what I'm trying to do here, but for now I'll live with it. 4, 5, 6, 7. I feel like this is too many. 1, 2, 3, 4, 5, 6, 7, 8. No, that's definitely too many. Again, the compiler would catch me if I screwed that up or whatever. 4, 5, 6, 7. 4, 5, 6, 7. Cool. So now I need to look at some AVX stuff. So mol PD, is that, no, that's for double precision. That's not what I want. Mol SD, no. Let's look at just AVX. Is this it? No, I think this is MM256. Yeah, okay, that's what we want. No, it's doing some other fancy stuff. I just want a plain multiplication. I filter by arithmetic. Well, it's already all arithmetic. All right. We've got some fuse, multiply, add. Those could be fun for a later time. Here we go. MM256, mol PD, and mol PS. All right. So we're doing this V mol PS, which I guess has three. Operands. Interesting. We bring back plain. If we bring back the plain SSE instructions, so mol PS only has 2 arguments. So it's multiply, pack, single precision floating point elements in A and B, store the results in DST. So yeah, not the most descriptive, but I think we're all right to just kind of think we're right to just kind of go for it here. So let's see what happens. So well, I guess we want add first, don't we? So this should be v add ps, right? V add ps result x, y. Well, maybe I don't actually need that. I can just do a batch 8. I can just have result be a batch 8 and kind of live with that. So maybe we just comment out everything for now and start with just addition. And we'll do float 8. So this is a batch 8 of float 32. And we can do 8 and 8 here. So probably some of these aren't going to work. Let's just comment them out for now. So we can do 1, 2, 3, 4, 5, 6, 7, 8. And maybe here we'll do 2s. Yeah, I'll see how that works. Invalid instruction mnemonic. Interesting. Maybe AVX isn't available for some reason. Like the JAI compiler doesn't know about it or doesn't know how to access it in some way. Let's see, add PS. Yeah, it's v add PS. Okay. Maybe I just call it regular add PS. Attempt to use polymorphic struct batch 8 as a value in an imperative scope. Okay, we've got other problems here. 32. Variable doesn't fit in register, size is 32. Okay, so seems to think that can you show me the description again? Okay. Add 4, 8, or 16 packed single precision floating point values from the first source operand. Yeah, you know what? Let's see what Godbolt gives us if I were to do this. So if I'm doing M256. That's it, right? M256. Oh, not 258. All right. Let's see. Oh, gotcha. Okay, so I've got to add AVX or something like that. Okay, yeah. So it looks like we're getting something like what we would expect to be able to write here. But I guess for some reason, JAI doesn't know that we're trying to compile with AVX features. So yeah, maybe we hold off on batch 8 for now. Okay, that's fine. So let's go back to float 2 and get that working for double precision. Cool. So, float 2 and float 2. Right. So now instead of float 32, we're going to do float 64. So if I go and try to do that now, it's not going to work because I haven't defined any of the operator overloads that we need to actually make that work. So let's see here. This is going to be batch 2 float 64. And again, I'll start with, I'll start with batch for float 32 is kind of my basis. Oops. And I guess another thing that would be good to test is that now I should no longer need the struct literals here, or the name struct literals, because I no longer have these kind of padded, these extra array elements here for padding. So let's see if that might work. Cool. So I'm just gonna do a little copy, find and replace action here. So this is going to be a batch to float 64. George says, why are you templating over T? I'm not trying to understand, like, why am I using T as the name for the template type? Like why did I choose T as that? So in Java, they call it polymorphism, which I guess could be kind of confusing coming from C++. But yeah, I just chose to name this T. Essentially this polymorphic argument T. And so then I'm choosing, you know, float 32 or float 64 to be that type. Yeah, I guess I don't have to. I could have named it something else. But yeah, I mean, I don't know. I could have named it like float type or something, but I might make batches of integers too. I don't know if I'm going to go through with that, but I might. All right, let's try double precision. So I think for this to work, I just need to do PD, right? Add PD. Oh, I don't want AVX here. I just want regular SSE. So I can just do add PD. That's the instruction I'm looking for. Kind of what I expected. All right, add PD. Add PD. Get rid of that. Oh, and then this should be float 64, even for the scalar here. Sub PD. Add PD, float 64. So yeah, this stuff should be pretty quick, pretty straightforward here. Nothing particularly fancy, just some retyping basically. PD instead of PS. Nothing too crazy here. All right. Division, float 64. Does div PD exist? Is that an instruction that exists? I guess we'll find out, won't we? Operator minus, I missed up one of the operator minuses. Float to x minus y. What's wrong with that? Float 2 is a batch 2 of float 64. Operator minus batch 2 of float 64 minus float 64, batch 2 of float 64 minus batch 2 of float 64. What's wrong with that? Type mismatch, incompatible specializations of batch 2. Struct parameter T does not match, wanted float 32, got float 64. But everything here should be float 64 now. No? I don't know, did I do something weird? Why didn't that error happen in the addition bit of code as well? So let's see if addition works on its own. Okay, it looks like even addition has problems. X plus Y. Batch 4 float 32. Incompatible, incompatible. Oh, I know what the problem is. I did not add this to my module file. So of course, there we go. Now it works fine. Cool. So yeah, I think we can just bring back in the rest of the code and it should work fine. All right, let's bring back in actually running that code now. Let's see. 1, 2 divided by 2, 2. Yeah, seems like these are correct. We can add some like actual tests for this at some point, but I don't feel like doing that right this second, so maybe I won't. Let's see. So now let's try batch 4. Well, so I gave up on batch 8 float 32 for now. Let's try batch, yeah, let's try batch 4 of float 64. If we can get those working. So basically we've got 4 batch types that work. Well, okay, right now we have 3 batch types that work. We can do batch 2 of float 32, we can do batch 4 of float 32, and we can do batch 2 of float 64. So let's get this last type working here, and then we can move on and maybe do something a little bit more fun with this SIMD stuff. So now I'm just resetting my test to work with batches of 4 numbers instead of batches of 2. And then the question is going to be, how am I going to do this? Given that now I've got registers that are 32 bytes wide instead of 16 bytes wide. So that's going to be the question. But I've got an idea, so we'll see if it's going to work. All right, so again, let's start with just addition, and then we can bring everything else in later. So right now it's not going to work because I haven't defined any of the required operator overloads. So let's do batch 4 float 64. And then let's make sure that we add that to the module. So let's see here. We're going to want to use kind of the same base operation here, the same add PD, but we're going to have to be a little bit more clever about how we do it. So we'll start by pasting this around a little bit. First things first here, we're going to want to extend that out to 4. Well, is that what we're going to want to do? No, we're not. We're going to want to do batch 2. And then we're going to want to define some, things here. So we're going to want x01 equals cast. We're going to cast this to a batch to a float 64. X dot x0. Right, and then we can do 0, 1. I think that'll work, but we might have to test it and see. And then I'm going to do something similar here. So yeah, I have an idea how this could work. So, well, actually, I may have to be a little bit more clever in both places than what I'm currently trying to do. So basically what I'm going to try to do is set up two batch twos that are kind of taken from this batch 4. So I'm taking the first half of the batch 4 and putting it in this batch 2, taking the second half and putting it in this batch 2, or really a reference to this batch 2 or a pointer, depending on how you want to look at it. And then I'm going to want, well, actually, I'm going to need to do the same thing with Y. So I don't think I've actually tried doing this in C++ before, or used a library that does something like this in C++ before. So I don't know exactly what kind of performance, we're going to get from doing this kind of strategy. But it'll be interesting. So let's see, batch 4, float 64. And we're going to want, so we're going to add, everything's going to be getting added into the X values here. So X dot X0, X dot X1, X23 dot X0, X23 dot X1. Yeah, maybe. Let's see. So this is Y broadcast. So we'll be doing, whoops. We'll be doing a similar kind of thing here. Oops. Except instead of having these actual Y registers, we're going to use the Y cast register. And then do the same kind of thing there. All right, let's try that, see what happens. Cannot cast from float 64 to a pointer. Okay, probably because I need to make those pointers, right? And I'm probably going to need to do some dereferencing at some point. A matching instruction form was not found. Okay, so I guess I want to like dereference these. I think this is like the new way of doing dereferencing in Jai. They made this change kind of recently, if I remember right. So I want to kind of, I want to be able to kind of reinterpret the X0 and X1 members as their own struct without actually having to create a new, without having to actually create a new struct and copy back and forth, Although I guess it wouldn't be the end of the world. No, because then I'd have to make another copy there. So I was thinking maybe I could create another like result batch, add stuff into the result batch and then return it. But the thing that I need to add stuff into has to be a batch 2. The thing that I'm returning has to be a batch 4. I don't really want to be making extra copies in between. So let's see, does Jai have something like a reinterpret? It appears not. I may not have a choice. That's a little bit annoying. Yeah, I mean, I'd rather not have to like copy stuff back and forth, but I may not have a whole lot of choices here. So let's see. What if I just do this, you know? So if I just do that and that, I don't know, see what it gives me. Okay, so it still doesn't like me actually accessing stuff inside the assembly block. So I need to basically have the stuff in the assembly block already be in the form that I'm going to mess with it in the assembly block ahead of time. Yeah, like I don't think I can actually, like I don't think I can dereference a pointer inside the assembly block. I wonder what is assembly for dereferencing a pointer. First line of code dereferences the base pointer as indicated by the parentheses. Okay, so maybe, yeah, maybe I could do this kind of parentheses and percent mark kind of thing, right? So let's see. If I do something kind of like this. Oh, interesting. Okay. Weird. Oh, okay. Let's just not do anything there for a second. Oh, gotcha. Okay, so it's still not happy. Does Jai have a how-to on assembly? I may need to have a look at that. I mean, my assembly in general is kind of rusty, so. Inline assembly, okay. Right, so we've got our different register types, and then we've got our general purpose registers, which probably are 64 bits, right? Let's see. Oh, okay, so you have to maybe tell it that you want this to be AVXable. Anyway, we'll get back to that. So broadcast gets rid of some broadcast instructions. Man, I probably should have read this before I started today, but that's okay. I learned something new. Okay. yeah, let's just read this from the beginning and start thinking about things from there. So same output. Instead of the intrinsics you find in other compilers, we provide functionality for robust inline assembly that tightly integrates with the rest of the high-level language. The compiler will produce the same output for your ASM code bit for bit every time. Note that we currently only target x86, so it's implied that you are working in that instruction set. This is not necessarily true, and when the time comes, other instruction sets will be added. Wonder when that'll be. We tell the compiler we're going to be writing assembly with the ASM directive. All statements in this block in the familiar mnemonic operand form. Here's our first instruction, a 64-bit immediate to the general purpose register GPR. The apple is our named GPR. We do automatic register mapping, so you can use familiar high-level names just like you do in regular programming. You can actually write that a bit more verbose since apple is actually inferred declaration in the same way that apple equals 10 is in the high-level language. The instruction selector finds a match, and in this case, we got a GPR. There's also an implicit size being used here. Traditional assembly specify operand sizes through the names of the registers. Since we don't use those names, the size is appended onto the mnemonic. Interesting. Okay, here's a list of available sizes. Byte word, D word, Q word, and XMM, which is mainly what we care about here. Since we're dealing in 64-bit mode, 64-bit operand size is the default implicit size when dealing with vector ops. Okay, you'll have to deal with your feature set. Here is the version that declares the register up front using explicit operand size. In order to make use of our hard work, we have to interrupt with the high-level language a bit. Here's our high-level variable. The variable has space on the stack and is also moved in and out of GPRs by the high-level code generator. With respect to ASM blocks, any variable referred to will be moved into the right GPR for you. In a release build, you can expect your variables to always be in the right registers, though it is a good idea to double-check code gen if you care. So here we're adding, okay. So basically we declare a variable. This is basically what we've been doing up to now. We declare a variable in the top level language, and then in our assembly block, we do some operation on it. ASM blocks aren't actually new scopes. The registers declared in them are visible in whatever scope the ASM block itself is in. It is possible for registers declared in ASM blocks to spill to the stack before being used again in a later block. This is up to the code generator. In practice, this only happens when there's contention with other high-level code. Okay. So basically here we're declaring apple and banana. Oh, I see. Okay, we're using the apple and banana that were declared up there. So that's kind of an example of how those registers kind of spilled over. Okay. Instructions are selected based on the mnemonic and operands provided. Instruction mnemonics are intentionally identical to the official mnemonic provided by Intel and AMD, so you can refer to official manuals when programming rather than having to go indirectly through something like the intrinsics guide. This also means we don't provide a listing ourselves. If instruction is not recognized by us, either we haven't implemented it yet or we missed it. Each instruction has a set of forms. Okay, so yeah, these are kind of the error messages that we've been seeing, right? So we've got memories, we've got immediate, and then we've got maybe something that's a GPR or memory register. One difference you will find with the official documentation is that there are not V prefixes on our mnemonics. In traditional assemblers, you will use the V prefix to indicate that you want VEX encoding for the instructions. Here, we determine if we use VEX based on the feature set. You will get the VEX encoded version of the instruction. Otherwise, we get the legacy version. More on feature sets later on. Okay, we'll get to that. As you know, immediate operands are encoded directly into the instruction stream, and different instructions use different sized immediates. Let's look at some basic examples. Okay, so we're using 8-bit immediates. If you try to value too large, compiler will tell you you're trying to use an IMM16, and there are no matches on the move.b instruction as you'd expect. Got it, okay. So that's for some move instruction business. It is ambiguous if you want 32-bit sign extended or 64-bit version when your value is valid. Okay, it doesn't support moves. All right, so just some things on immediates. I'm not sure we'll have to deal with that a ton. The register allocator has some smarts and takes things like lifetimes into account. This lets you use new names to convey data flow the same way you would in high-level code. As a result, register management is turned into a working set size problem rather than an annoying bookkeeping one. If you ever exceed the maximum number of alive registers, you'll get an error from the compiler. There is no automatic spilling or other magic going on here. Gotcha. Okay. So you have GPRs, we have stack registers, vector registers. I imagine we'll get to those at some point. Sometimes you need to be a bit more explicit about which location registers get mapped to. Oh, gotcha. Okay, so we're saying A is pinned to a GPR. That's interesting. Okay, some implicit registers, and then memory. So here's kind of what I was looking for. In x86, there are also memory operands on the form base plus index times scale plus displacement. To indicate a memory operand, you wrap it in brackets, just like you would in a traditional assembler. The ordering of the expression is considered rigid, and that you cannot place the displacement first or the base second, etc. This is to reduce confusion, since most of the fields are usually ambiguous identifiers. Here's some rules: base, index, scale. Okay. So for example, we have an array. We have a pointer into the array. We have an index, which I guess we're going to index into the array as well. Not sure what we need those for, but probably something important. We load B and I with some valid data since we don't want to crash the how-to when running. Okay. So we put the pointer and the array index into B and I. Now we're going to move B into T, I guess. Move other things into T. All right. Fair enough. We can also refer to high-level vars directly in all four of these slots. The scale and displacement must be constant. Oh, I see. Okay. Yeah. I'm not sure what this displacement is. I think it's just, seems to me like it's just a random thing, right? Like it's minus 20 plus 13. I don't know if that really matters. To take that a step further, we can put these expressions in line by wrapping them in parentheses. Oh, that's neat. Okay, cool. There are a few limitations with the current system with versus stack address, and you cannot directly access variables that only exist on the stack via a memory operand. You also cannot access variables in global scope. These limitations are due to the current architecture and integration issues with LLVM. Interesting. Not much of a functional problem. It just means you have to manually load a raw pointer with whatever you were trying to access beforehand. Gotcha. Okay, so with this, I think we can do what we wanted to do here, right? Basically, we would do what we were trying to do with this business here. So we would do our brackets. Oops. Instead of the parentheses that I was trying to do, which I guess I just copied from Godbolt, but it must be something different. A matching instruction form was not found. GPR mem was provided, but expected one of vec. Gotcha. Okay, this is probably because this is looking at U8s, which can fit in a GPR. I don't want that. I want an XMM word, right? Yeah, I want an XMM word. Cool. So let's see here. So what's the right way to do this? Okay, yeah, so this is how we would check to see if AVX is available. That's kind of cool. But yeah, obviously we don't want to do that. We don't really want to do that in our operators here. We want to have that saved and make that decision at an earlier point in time. Okay, then we've got our advanced features and whatnot. So let's see. What if I do move dot x t x01? What if I do that? Are we happy with that? No, we're not. Move doesn't support size X. Right. Okay, so this is kind of annoying because I've kind of already got like the things that I want to operate on here. Right. Yeah, like I could do these fancy moves, but I don't really want to. What if I do move double word? Yeah, I think that would be closer to what I want, right? I think it's that, right? Moving it into T. Yeah, there we go. Okay. So let's see now. Maybe I can add like that. Can I add to T? Ah, apparently not. Okay. In fairness, my assembly skills are a little bit rusty, but you know, still no excuse. I should be able to do this. Let's see if I do tx and ty, am I able to add ty into tx? Apparently so. Still not actually working, but we'll get there. All right, so now I want to write back into x01. Oh, also this should have been y01. Yeah, so this should be I think I can just do this. Maybe. So it allowed me to do that, but it didn't seem to actually give me the result that I was hoping for, because yeah, when I look down here, it doesn't seem like I actually got anything like I wanted. I also wonder, what if I try putting the pointeriness in there? What if I parenthesize? Okay, it doesn't like that. Yeah. Okay. Let's see, x01. All right. So Yeah, I guess the other thing is that there's probably some simpler ways to do some of the stuff I'm trying to do here, but that's okay. I can work that out. So what if I just try to print well, can't type today. What if I just try to print TX in here? Is that gonna work? Something tells me it's not, but you know what? Never hurts to try. Let's try that. Okay. Error, undeclared identifier print. Oh, right, because I need. Let's put it at the bottom here. Only I can spell. All right. Let's try that. Okay, segmentation fault. Someone's not happy. Maybe because I need to dereference this. Registers cannot be accessed by high-level code, only using an ASM block. Okay, I guess that makes sense. What if I just try to print x01? Okay, so that contains 1, 2. So that didn't change from when I defined it here, right? So I defined x01 there. And then when I tried to move something into it, it didn't work. So what if I just try to move like 400 into it? I don't know. See what that does. Ah, okay. Apparently nothing good. All right, so what if I do what if I just do this? What if I just do a batch to float 64 and we'll call this ZZ, and I'll just put the result of my addition in ZZ. So basically I'm just doing TY and adding that into ZZ. Oh, and then I want to print ZZ, don't I? So this should be equal to 1, 1. That's not, right? Because I should be doing that add there, which should make it 1, 1. But I'm not getting that, which leads me to believe something weird is going on here. So what's in Y01? It should be 1, 1. Yeah, okay. But for some reason, when I try to dereference it here and move it into that block, or move it into that register, it's not working. Okay. Well, maybe we want to treat this in kind of a different way. Maybe I spent too much time trying to avoid copies, and they're really not that bad. Let's just do some copies. So let's see. X2 is equal to batch 2. Yeah, because I think really what we're going to end up with is either a bunch of copies or a bunch of moves. And by moves, I mean like these move instructions here. So if I'm going to do that, I might as well just do that in the higher level code, and I think it'll work out to be more or less the same. All right, so we'll do that, and then we'll do Z. I'll call this Z first. This would be batch to float 64. Right, and so we'll just do, well, you know what? Let's do it this way. So I'm putting the y variables into some random batch that I'm going to throw away. And then I'm putting z first. I'm putting the x variables into z first because that's what I'm going to be returning essentially. So z first, y2. And then here we'll be returning the values from z first. Oh, okay. Let's just do zeros there for now. Cool, there we go. Yep, so we've got the first bit of stuff working. Wonder if I can put these in one line. Maybe that would be a little bit nicer. So now we'll assign to y2. Oops. The second, so now we'll do the second half of the 4 numbers. So 2, 3, second, and now we can just put these in here. So yeah, again, I don't know exactly what kind of performance situation we'd be looking at here, but it seems to work. So I'm going to go with that for now. And yeah, let's see if we can get the rest of the addition operations working. So let's see. In this case, there's probably some easier tricks, right? So yeah, we can just do this y cast. And then we don't need to do the y2 copies and from here. All right, so those can go away. And we can just add y cast instead of y2. And that should work. All right, let's try it. Cool, yeah, so that seems to work. It ended up being a little bit more difficult than I would have expected, but it does work. And most likely, we can probably even get some AVX stuff happening if we feel like going that route. So yeah, then the question would be, how do we pick whether or not to use the AVX implementation in a smart way? So I'll put that in my list of to-dos. Yeah, and I wonder too if like, I don't know. I wonder if doing these like combined batches is even like all that useful from a performance standpoint. Like, is it even worthwhile doing like a batch 4 kind of thing as opposed to just doing a like some kind of thing where you're only some kind of thing like the way SIMD does it, where the only types that you're provided are types that are explicitly mapped onto one SIMD register. I'm also a little bit curious if I'm able to add things like, for example, if I wanted to have like a sort of like what we'd have like a const expr thing in C++. Is that okay? Well, I'm sure it's fine in that regard. And then what if I go back to 32. Are we still okay with it? Apparently we're still okay with it. What if I make it non-constant? Now we should no longer be okay with it. Yeah, okay. So long as I keep that constant, seems like we're fine. All right. Actually, let me double check one thing with this. So if I go to here and I just satisfy the struct literal, are we still okay with it? Oh, maybe not. Here we go, batch 4 float 32. Whatever. Yeah, there we go. So now we've got a 24 byte versus 16 byte mismatch. Cool. Okay. Whereas if I bring this back to a constant, oh, this should be 4 actually, then everyone's happy. Cool. All right, yeah. Well, there we go. So that's a little bit of SIMD for today. Yeah, I'm gonna have to think a bit more about how I want to design this library and how I kind of want to get things working for different batch types and different instruction sets and whatnot. But yeah, I think that's all I'm going to do for today. There's going to have to be a good bit more work that gets done before this becomes even remotely usable. So that was kind of a fun, starting point and just kind of exploring and seeing what we can do. But yeah, I'm excited to keep experimenting and seeing what can be done there. Yeah, so that's all I've got for today. I'm not going to be here next week. I'm going to be out of town, but probably the week after that, I'll be back with another stream. And yeah, I'm not sure what we're going to do, but it'll be something fun and interesting. So yeah, thanks for tuning in, and we'll be back in a couple weeks.